You step into an elevator. The doors close. But you're not going to the 50th floor. You're going to space. 35,786 kilometers straight up. No rocket. No explosion. No G-force crushing your chest. Just a cable, thinner than a human finger, holding you between Earth and the stars. This is the space elevator. The single structure that could eliminate rockets forever, cut the cost of reaching orbit by 99%, and open the solar system to humanity. Or, if it fails, wrap around the entire planet like a whip of God. Today, we imagine what happens if humanity actually builds it. Every bolt. Every cable. Every catastrophe. Here's the physics. At exactly 35,786 kilometers above the equator, objects orbit Earth once every 24 hours. They hover over the same spot forever. That's geostationary orbit. That's where you put the top. But the cable doesn't stop there. It keeps going, another 60,000 kilometers past geostationary to a counterweight. Earth's own rotation flings this counterweight outward, like a ball on a string. That centrifugal force is what holds the whole structure up. No supports. No pillars. Just physics and tension. The bottom anchors to a floating platform on the equator, likely the Pacific Ocean, where weather is calmer and hurricanes are rare. Let me give you scale. Mount Everest, 8.8 kilometers. The International Space Station, 408 kilometers up. The space elevator, 35,786 kilometers to geostationary, and 100,000 kilometers total. That's 1/4 of the way to the moon. And every single meter of it has to be perfect. Because the moment any part of this cable fails, the most catastrophic event in human history begins. Here's the problem that has stopped every space elevator concept since 1895. A cable this long has to hold its own weight, 100,000 kilometers of it. The tensile stress at geostationary orbit reaches 62 gigapascals. Steel snaps at 0.5 gigapascals. Kever, 3.6. Still nowhere. The only material that theoretically works is the carbon nanotube, a cylinder of carbon atoms with a tensile strength of 100 gigapascals. A single nanotube is 100 times stronger than steel at 1/6 the weight. In practice, the longest continuous carbon nanotube thread ever made is under 50 centimeters. We need 100,000 kilometers. That's a factor of 200 billion. The defect rate in current nanotube production is catastrophic. Even a single atomic misalignment reduces strength by 40%. One flaw. One atom in the wrong place. And the entire cable snaps. The space elevator isn't an engineering problem. It's a materials science problem. And we are orders of magnitude away from solving it. But let's imagine we do. Let's assume the material miracle happens. The cable is built. Now the real nightmare begins. Construction starts in reverse, from orbit, not the ground. A single rocket delivers a spool to geostationary orbit. The spool unrolls cable downward toward Earth while simultaneously extending upward to an asteroid counterweight. When the descending cable reaches the atmosphere, a chase vehicle catches it and connects it to the anchor platform. Then the climbers begin, robotic crawlers riding the cable upward at 200 km per hour, depositing additional layers of nanotube ribbon with each pass. Construction takes 20 to 30 years. Total cost, between $10 and $20 billion for the first elevator. Cheaper than the ISS. The geostationary station becomes humanity's busiest port. But first, the elevator has to survive the planet it's attached to. Hurricanes. lightning, space debris, radiation. And the worst one, the elevator is the single most strategically important structure ever built. Whoever controls it controls access to space. A single anti-satellite missile could sever the cable. What happens when it breaks? The break point determines everything. If it happens above geostationary orbit, the upper portion is flung outward by centrifugal force and escapes Earth entirely. The lower portion falls. And because Earth rotates underneath it, the cable doesn't drop straight, it wraps. A 25,000 kilometer ribbon of carbon nanotube draping itself around the equator at supersonic speed. It hits the atmosphere and doesn't burn up. The kinetic energy is almost incomprehensible. Anything directly under the falling portion is obliterated. The equatorial band, Ecuador, Kenya, Indonesia, suffers the worst artificial disaster in history. But the nations of Earth would build it anyway. Because the upside is too large to ignore. At $10 per kilogram to orbit, the entire economics of space flips. Space tourism becomes a $10,000 ticket. Asteroid mining becomes profitable. A single metallic asteroid contains $10 quintillion in raw materials. The elevator makes capturing and processing these asteroids economically viable. Earth's resource scarcity ends. Mars colonization accelerates from science fiction to construction schedule. Spacecraft released from the elevator's top don't need rockets. They're flung to Mars, the asteroid belt, even the outer planets, using Earth's rotation as a slingshot. The first elevator enables the second. The second enables the third. Eventually, a ring of elevators spans the equator. Orbital solar arrays beam clean energy to the surface 24/7. The energy crisis is solved from above. And here's what nobody talks about. Within a generation, the orbital station becomes a permanent city. Children are born in orbit. They grow up in zero gravity, their bones lengthen, their hearts reshape. They can never come home. Earth's gravity would crush them. They are the first post-humans, not through genetic engineering, but through infrastructure. The space elevator isn't just transportation. It's a speciation engine. The moment the cable is completed, humanity begins to split, between those who stay and those who leave. Between gravity and freedom. The space elevator isn't just a way to reach space. It's a test of whether we deserve to. And the answer isn't found in the cable. It's found in us. If humanity actually built a space elevator, would you ride it, knowing the risks? Drop your answer in the comments. The most upvoted response inspires a future Imagine IF deep dive. Next week, what if a second sun appeared in our sky tomorrow? The first 8 minutes would be fine. Minute 9 would end everything. Imagine if